Hello everyone, I'm Zehuan Wu from Airtrack in Monash University. The topic of my talk is the statistics and scaling of Couette Poiseuille flows at the verge of separation. The Couette Poiseuille flow is the flow between two walls. A draft of the flow is shown here. In the Couette Poiseuille flow, one wall is moving at a constant speed, and the other wall is stationary. So the flow is driven by viscous force and pressure gradient. In my study, the adverse pressure gradient is applied, so the stationary wall has zero mean skin friction. This special Couette Poiseuille flow is set up for the study of a wall-bounded turbulent shear flow with zero mean wall shear stress. Besides, this flow has some advantages compared with adverse pressure gradient turbulent boundary layers. For example, it has no historical effect after fully developed, and the entire domain can be used to collect the statistics because the flow is self-similar in the streamwise direction. So this talk will show some results about the characteristics of a Reynolds shear stress on two walls in Couette Poiseuille flow. We use a fully resolved DNS database obtained from our in-house DNS code. The Reynolds number is 3000 based on the velocity of the wall and half height between two walls. The friction Reynolds number on two walls are Re tau S and Re tau M. The subscripts S and M indicates the stationary wall and the moving wall. So we can see the skin friction on the stationary wall approach zero compared with that on the moving wall. Lx, Ly, and Lz are the size of the computational domain in the streamwise, wall normal, and spanwise directions. Nx, Ny, Nz are the number of grid points. Delta x plus, y10 plus, and delta z plus are the grid spacing in the friction viscous length scale of the moving wall. Those parameters are defined here. So in our study, we set two reference frames fixed on two walls to observe the statistics. The mean property observed on the stationary wall is labeled with a subscript S here. On the moving wall, it is subscripted by M here. In this study, we use the quadrant splitting scheme and the flow topologies to characterize the Reynolds shear stress. The flow topologies are based on the invariance of the velocity gradient tensor. Basically, it classifies flow structures into four non-degenerate topologies, which are compressing vortices, stretching vortices, stable saddles, and unstable saddles. So we can know each small volume in the fluid belongs to which topology by this method. On the moving wall, the mean streamwise velocity in friction viscous scale is shown in the left figure. We can see the profile collapse to the linear scaling law and the log law. Basically, the mean flow near the moving wall is similar to a channel flow. The figure on the right-hand side shows profiles of the Reynolds shear stress contributed from four quadrants. On the moving wall, we can see sweeps dominate ejections below Y plus around 15, which shows turbulent kinetic energy in this region is transferred from higher position. Above Y plus around 15, ejections become dominant. So turbulent kinetic energy is transferred to higher position by ejections. The cross point here is where the production of turbulent kinetic energy reaches the maximum in the entire flow. These figures show the Reynolds shear stress contributed by sweeps and ejections on the moving wall associated with flow topologies. Based on the study of Robinson, the burst phenomenon is carried by quasi-streamwise vortical structures from buffer layer. So we observed ejections dominate sweeps over buffer layer, and they are mainly associated with compressing vortices and stretching vortices, which is in agreement with the Robinson's results. Then let's have a look at the flow on the stationary wall. On the stationary wall, U tau approach zero, So in this situation, friction viscous scales are no longer applicable. So we use the pressure viscous scales for normalization, which are defined here. In the left two figures, we can see the mean streamwise velocity profile on the stationary wall follows two scaling laws. One is the quadratic law proposed by Stokes and Henningsen, and the other scaling law is the square root law proposed by Stratford. These two scaling law was proposed based on the assumption that the gradient of the wall shear stress is balanced by the pressure gradient. So the square root region and below are the domain of interest on the stationary wall. So in the right figure, we can see the Reynolds shear stress on the stationary wall is dominated by sweeps in all layers, which is the main difference compared with the flow on the moving wall. A good thing in the critical positive flow is that the mean wall normal velocity is 0. So the dominance of sweeps over ejections means the amount of turbulent kinetic energy going down is greater than the amount of turbulent kinetic energy that is lifted. Besides, the flow on the stationary wall barely produces turbulent kinetic energy locally because of the 0 mean skin friction. So the flow needs turbulent kinetic energy from somewhere else to sustain turbulence. In the critical positive flow, those turbulent kinetic energy mainly comes from the moving wall by sweeps. These figures shows the Reynolds shear stress on the stationary wall contributed by sweeps and ejections associated with flow topologies. You can see there is no near wall peak on the stationary wall, which indicates the burst process may not exist because there is no much turbulent kinetic energy produced locally. Besides, sweeps and ejections are mainly associated with the saddle topologies in the buffer layer, which is different compared with the flow on the moving wall. In the square root region, the dominant flow topology becomes stretching vortices, which may result from the local shear stress, because in this region, local shear stress is a bit stronger than the near wall region. We can draw a typical conceptual model. The left model was proposed by Robinson, which shows sweeps and ejections associated with the vortical structures in canonical flow. In the right-hand side, it shows the sweeps and ejections with the saddle topologies, which is our explanation about the association on the stationary wall in our case. After these observations, we can draw some conclusions. First, the Reynolds shear stress on the stationary wall has different characteristics compared with that on the moving wall, due to different mechanism of sustaining turbulence. Second, the turbulent kinetic energy is barely produced on the stationary wall, and it is mainly transferred from higher wall normal position by sweeps. Third, on the stationary wall, sweeps dominate ejections in all layers. Below the square root region, sweeps and ejections are mainly associated with the saddle topologies rather than vortical topologies. That's all about my talk. Thanks for listening.